We're on chapter 4. Where is that? All right, and we talked last time about the independence of XY motion. Buffering. All right. And let's have some fun to start out. Get this grouchiness out of my system. All right. I want to look at problem 4.22. 4.22. Yeah, that's the upcoming stuff. Okay, there's a gun of some kind. And there's a projectile that's going to come flying out of here with some speed. Did I call it V0? Yeah. Right over here is a duck, or a monkey, or some kind of creature. Let's make this creature just some kind of amorphous blob. We'll call it a duck. All right. Now, the idea is I'm going to have a sensor here, right? Or you could pretend that the duck has really excellent hearing. And the idea is at the instant that the bullet comes out of the gun, the duck will hear it and let go of the branch. Okay? So if it helps you visualize this, oops, wrong way. We've got a duck. Okay, here is our duck right here. Now, in this case, here, whoops, oh. Here is our gun. And instead of this duck, which is inanimate, hearing the sound, what I've got here is a little Photogate sensor. So the idea is the instant the ball comes out of the gun, whoops, did it just fall down? Yeah. So the reason why is I hit the sensor. If you look, right when I break the beam, we see that the duck will fall down. So the idea is as soon as the ball comes out of the gun, the duck's going to fall down. Everybody cool with that? And then what you're going to have to do for me is aim so that you're shooting it. Or we're going to have the class decide where you should aim. So the question is, where to aim? Does everybody understand the question? You're going to shoot at the duck's going to let go the second the ball comes out of the cannon. Do you aim above the duck, at the duck, or below the duck? Take a second to discuss with your neighbors. And then we'll take a vote. Which way do you think you should aim? Go ahead and talk for a second, and I'll get this approximately lined up. You guys remind me to activate it. I'm going to turn off the activate. Okay. Just say did you activate? We get ready to shoot. Okay. Okay. Keep talking. All right, let's go ahead and take our vote. Where should we aim? And it's okay to be wrong, but it's just more fun if you participate, and you supposedly will remember the answer better and the reasoning behind the answer better, even if you guess wrong. That's what the science indicates, the educational research. So take a guess. Where do you think you should aim? How many think above the duck? Okay. A lot. How many think you should aim at the duck? Couple. How many think you should aim below the duck? Most. What have we learned about students' intuition in physics? You're usually wrong. Okay, let's find out. Okay, you ready to aim? My claim is you should aim directly at the duck. Okay, and let's have it. Let's see if I'm lying to you here. Just a second. I'll help you. Okay, and let me go down just a little bit here. Okay, whoops. I like how there's this red vector here in the background of this thing. All right, so now what we've got here, there's a sight back here, and there's a sight right here on the end. So the idea is if you could line up, you see how there's a little hole there? Yeah. There's one right here too. So if you can look through both holes, that's where you're aiming. So what I want you to do is try and look through both holes and try and aim it at the duck. Does it look kind of close or not?
It looks like right at the.
Does it? Okay. No bumping up or down, left or right. Is it kind of close?
It's like right this part.
Okay. All right. So you're aiming right for the belly here?
A little bit below.
A little bit below. Okay. So let's bump it up just a hair. Try that. Is that better?
Yeah, that's like right below.
Right at his beak?
Yeah.
Okay. All right. Let's tighten this down. All right. Now here it is. I will activate it after I load it. So the trick is there's an activate switch here. I switch this to inactive so I can mess around and load the gun. Then we're going to activate it right once we're about to shoot. Thank you for reminding me. Okay, now wait, I need to activate. Okay, so this is how you pull the trigger. You just stand up and pull. And then maybe stand to that side. Let me see if it's going to show up on Zoom at all. Yeah, let's go for it. Okay, look straight up. Did it hit the duck or did it shoot to the side of it? Was it shooting that way a little bit? All right, so then we got to rotate it just a little bit. Not like that. Let's try one more time. And then, so that we have better contrast, hard because it's easier to see. We're gonna have to realign this thing. There we go. Now it should be easier to see. I don't know where that other yellow ball went. If somebody sees it, let's go ahead and try and line this up again. We'll hit inactive. One more shot. I'll double check too.
That's right to the left.
So we need to go like that.
No.
Right. What about there? How about up and down? Shooting straight for the center.
No, it's kind of like hitting at the corner, like the bottom corner.
Bottom corner. All right. All right. So tap it, kind of move it around. See what we can do here. Is that better? Now, which way? Like this way?
No, there's more. Yeah.
Right there? Can I double check? Can I get in there? Just double check. That was pretty close. Can you confirm that? Go ahead and look at the site.
Yeah.
Okay. We gotta be careful not to bump the table or anything. Let's try this again. Okay. Put your hand on top of here too, so this doesn't jerk. Push down hard. Yeah. Go for it. Agree? We aim straight at it. We hit it right in the middle. Everybody cool with that? Live. Let's give him a round of applause here. Yellow ball all around. Just grab it for me sometime. All right. This is supposed to be a reminder of the following. First, let's imagine that there was no gravity at all in the universe. If you shoot the ball this way and the duck lets go, if there's no gravity, what would happen to the duck? If there's no gravity,
You'll stay there.
what would happen to the bullet?
You'll just keep going.
It would go straight at it. So if you aim straight at the duck, you would imagine you would hit it if there was no gravity. Well, now the issue is, in this case, the duck should start falling, right? And it's going to fall some distance. Delta y is equal to the initial y, t, plus 1/2 a sub y, t squared. The initial is 0. This is going to be negative 1/2 gt squared. Agreed? Well, think about the delta y equation for here. Another marker. There. Cheating a little bit here. Look. Oops, I forgot a t. Think about this case. The idea is this v0 sine theta t, that's the straight line path. This is the amount it will fall below the straight line path. It's exactly the same as how much the monkey will fall, or the duck, or whatever the hell it is. In this case, the idea is this part is 1/2 gt squared with a negative sign because it goes downwards that much. Whereas this bit right here, well, actually, excuse me. This bit right here, the whole thing is this v0 sine theta t. So once again, this is supposed to be a reminder that the x motion and the y motion are independent. I don't know, I find that slightly interesting. I don't know if that made sense to you, but this is just a reminder that yes, we really can, in all these instances, treat the y motion of this independently from the x motion, right? The v0 cosine theta t, that just has to do with here. Well, what if I shot this faster or slower? Do you think that would matter? That doesn't affect this term. So this should work even if we shoot this at really low speed. The only difference is if we shoot this at low speed, what's going to happen over here?
It'll take longer to get.
It'll take longer to get there. And so if you shoot it at slower speed, it'll be closer to the ground. And if you wait too long, it's going to hit the ground and screw up the problem. Agreed? Or another thing that could happen, if you shoot it too slowly, it might not have enough energy to get there. When I was a kid at your age at school, they actually brought a real rifle into class. They didn't bring a real monkey or duck, but we had a can. And then the instructor was shooting guns in class. It was a different era, as you know, right? You know well about all that. Anyways, pretty crazy, right? I hope that was slightly fun. Okay, so that's our warm up for the day. Any questions on that? If you're passionate about seeing the math, you can look at the math and do it yourself, okay? So you could do that problem at home if you're really curious about it. What I'd like to do is get into a two-dimensional word problem that has constraints. Okay, in particular, I want to look at 4.23. Okay. Screw this up. I'll get there in just a second. Just a second. Seemingly work with physics textbook. Okay, you got it? just setting up the demo. All right. See if I can show this to Zoom. If not, we'll try our best here. All right. Oops, wrong way. Okay. Now, I don't know if you can see this, but take a look here. I've got this projectile launcher right here. We're going to shoot a ball out of here. And now, this long ramp that you can see here, I want you to think of that like a mountain. How convenient that we're at the Winter Olympics right now, right? We can actually pretend we're doing a Winter Olympics special here in physics. What's that? Yeah, that's right. That's right. Which is weird because no one's ever accused me of being relevant. But yeah. All right. That's good. All right. So in this case, this is what I was thinking about. Imagine you're a ski slope designer. Okay. And you want to figure out, man, I want my Olympics to be action-packed. I want really big jumps. Well, the question becomes, what angle should you have these? Now think of this as the ski jumper is going to be like the projectile here. Right? So there's going to be a ski jumper flying off some ramp. And our question is, which way should I angle the ramp, or sorry, angle the ski jump ramp so that the skier goes as far as possible down the mountain? Now think about this. When you're going to design a ski park, you pretty much you're not going to change the mountain, right? The only thing you can do is change the angle that people jump off the mountain. So this is what we're trying to optimize. I'm going to get this up on the board, but hopefully this visual helps you see that. All right. So that's going to be our goal. You can now reread question 4.23. Trying to use our ability to do kinematics problems to solve a practical issue that a ski slope designer might have. Sounds ridiculous. So the skier is going to come down here and jump off some ramp. I'll draw the skier as a ball, and this skier is going to have some initial speed, V0, and some launch angle, I'm going to call it theta. There's going to be multiple angles in this problem. You better be careful how you draw them. In particular, I think in this problem, I chose to label this angle phi. This is the angle of the mountain. Normally, that was our impact angle. So I want to emphasize, and the reason I did this is because in most textbooks, when you see a problem like this, there's going to be some impact down here. I'm going to call this impact angle psi. And this is just the notation I chose to use. I apologize. Normally we'd be calling this phi. So psi kind of looks like a saguaro cactus if you want, or a trident, something. Just look, we got three angles in this problem. We better be careful here how you write it. Everybody clear? There's a difference between phi and theta. What do we know? Okay. Air resistance is huge, but we're going to ignore it, right? Air resistance is probably one of the crucial factors to help these people ski, but we are ignoring air resistance. Let's write that down. We know, let's write down what are our givens here, just so we don't get lost. Givens. Looks like we know V, theta, and phi. And we know the distance L down the slope. I don't think psi is known. right? Psi is not known. And it's not phi either. In general, just because you have a certain mountain with an angle doesn't mean that's going to match your impact angle. Now, if you were designing half pipes or moguls, it turns out you kind of want that to be true or skiers break their legs. So there was a lawsuit a couple of years back. Somebody that designed the moguls screwed up the impact angle and didn't realize, oh, my mogul's got this angle and didn't have the right impact angle. So people were getting injured. In general, though, we don't know that these two are equal. So far, so good on that? Oh, come on. All right. We do know this distance here is L. The length they make it down. So we're told, okay, we want this person to get down the ramp L. So first, what is part A of this question? Show downslope range equals this. So we're supposed to show this. Now, from experience, students do silly things when they're first starting physics classes. When they see this word show, they'll be like, oh, assume this is a known fact. The idea is you're supposed to do the problem, and whenever you see a physics problem that says show this, that's basically saying this is the answer you should get if you do your standard procedure. Okay, you're not supposed to take this and plug it in and show it works. You're supposed to prove this. So perhaps a better way physicists could write these questions is prove that's true, just so you know. All right. What could we do to start learning about this? Any ideas? I did the first part of the problem solving strategy, drawing. What's the next part? Make the charts. I dig it. I'm going to run out of room here, maybe. Maybe what I'll do is I'll put the delta X on this side and the delta Y over there, just because I'm going to run out of room on Zoom. Let's try that. Delta X, the initial X, the final X, A sub X, T. All right. And over here, I'll do delta Y. And I don't need to rewrite the time variable because it's the same for both. Agreed? All right. So we're faced finally with a realistic problem. We're ultimately, right, because once we prove this, we can use this to analyze the angles. Any ideas for any of these parameters at all? Anybody on Zoom you can speak up to, or in class, any of these parameters that you would know? We're talking about a ski jumper flying down a hill. What's that? What is delta X? It's not L. What? Well, let me rephrase. What coordinate system are you assuming? Are we assuming a normal coordinate system, X and Y, just the normal direction? Well, right? Isn't this our normal XY coordinate system? So is delta X equal to L? No. What is it?
L cosine phi?
Yeah, nice. Do you agree the length of this side should be L cosine phi because this side's L SOHCAHTOA? Did that make any sense? Nice job, whoever that was. All right. What about V initial X?
And we be cosine of theta.
V cosine theta, and we called it V naught, so we're going to do that here. Notice how crucial it is to keep track of your thetas and ph's. What's V final X? Do we know it or not? Why is it the same as initial?
Because x and y variables are independent.
And
And so the x doesn't change as you're going along, but y does because the x direction doesn't have any acceleration.
yes, AX is 0, right? Because gravity's only up and down. So I guess what else we're assuming here is AX equals 0, AY equals what? For a projectile? Nope, negative G. G is the size of it, negative for the opposite the direction of the coordinates. Does that make sense why I have negative G here? I'll put that in here, negative G. And then somebody told me this isn't going to change. If there's no acceleration horizontally, this isn't going to change. Do we know the time? I don't think we do. All right, let's go over here. What's delta Y?
L sine of phi.
No. Why is it not L sine of phi? You, right? Look at this side of the triangle. What's the size of this side of the triangle? L sine phi. So do you agree this side of the triangle? Oh, geez, I keep right sideways right now. Give me a sec. That's the size of it. Did you go up or down in the ski slope problem?
You went up for
You went up. No, at the between here and the final position. What is okay. Let's remind ourselves. What does delta Y mean? Remind me what delta Y means in physics. Displacement, not distance. So what is your displacement between this point and this point? Negative L sine phi, right? Now, you're right. The distance traveled, you'd have to account for the up and the down and the arc length, and no, we're not doing that. Is that cool, the subtle difference there?
Yeah.
Sneaky, right? Minus L sine phi. And I don't know if you've noticed, it's all in the minus signs for these problems. If you screw up one minus sign out of 3, you get it wrong every time, and then you're frustrated. So that's why I'm harping on these minus signs. What's V initial Y? Yeah. V final Y? I don't know right now off my top of my head. So far, so good. This is the deal. And we've done this a couple of days in a row. So hopefully you're starting to catch yourself and always be watching your signs. And that was the goal of that setup. So far, so good. All right. So in this case, what's the next step of our problem solving strategy? We've drawn, we've labeled, we've listed some assumptions, some knowns, some whoops. What's the next thing? Equations, my bad. All right, sorry. Okay, what's the only equation that has any use in a standard projectile equation for the x direction? What's the only equation? First one. All right. Do you agree the other ones basically give us V initial equals V final or V initial squared equals V final squared? Do you remember that? If not, you could write them out and show it. All right. What are our equations for the y direction then? I just plugged in that AY equals negative G. I didn't plug in anything else. Maybe I'll write that. All right. In case you're wondering where I got that from. And here, I guess I could have plugged in the V0 sine theta and stuff like that. So I apologize if I plugged in some stuff and not all of it. What was our goal?
To prove that L equals 2 square cosine.
To prove this jump. All right, how are we going to do that? Any ideas where we should start? We could find t. Which equation looks the easiest for finding t? Let's just do a quick check, like right down here. Do I know b final y? Do I know t?
No.
So that's not going to be a good place to start. How about this one? That looks kind of ugly. Do you agree? Right? In theory, we could figure this out maybe. But we're looking to prove that L equals something. So L, yeah. Be careful here. Now whatever. I'll call this partially known because that's what we're trying to prove. So which equation might be the best?
The top
First
one.
one, right? And if you're not sure, you might just play around a little bit, right? But getting some experience doing some homework problems is what's going to help you. So in this case, t is equal to, what was delta x? L cosine phi. All right. We're getting close, right? Now that we know time, what could we do?
Plug that in for the like equation.
Okay, let's see what that does for us. Very oftentimes, this is useful. I'm not saying this is going to work for you all the time, but in a huge number of cases, we're going to take t and plug it into here. Now, you could be saying, isn't that just a trajectory equation? You're right. If you happen to have the trajectory equation memorized, that would have saved you a step. But I don't like memorizing things, so this procedure works great. Not to mention, if you solve for t, we could probably plug into here and learn something about the final velocity later. So I feel like this is a good procedure to learn. All right, so what we're going to do is we're going to try and use this t in here. And so I have some space to work. I'm going to maybe erase these because it looks like I'm not going to need them. So just for Zoom purposes. Now, if it was on your page, I would leave it on there, but because I have limited whiteboard, I got to do that. Well, let's see what I get here. Minus L sine phi equals V naught sine theta times V naught cosine theta. Wait, did I flip it upside down? Check the units. This is the one I told you I always flip upside down. You see it? Did I flip it upside down? Yes, we would have caught this when we checked the units. I'm terrible with this equation for some reason. I get in a hurry. You agree it's upside down. We were wrong. Sorry about that. Let's fix that up. It should be x over v naught cosine theta. I tried to do too much in my head. And I've been doing this 20 years and I screwed up, right? So if I'm going to make these screw ups, you will too. That's why it's important to do it on paper. I apologize. Should be delta x over v naught, which should be L cosine phi over v naught cosine theta. Apologies for that. I could tell when I plugged it in right here because I was checking the units in my head when I plugged it in. That's why I noticed it right here at this step. So I know that seems silly to check the units, but oh my gosh, think if you did all this algebra and forgot to check your units. It's going to get ugly. You would not be happy. Okay. That looks a little better to me. Now I can see, look, the units are going to drop out. The meters per second drop out, and I get length equals length. That's how I caught my mistake. Bad Rob. Is that good or not? squared. Good. If you want, you can check the units of this term too, right? Let's do that really quick. Meters per second squared. I got meters squared over meters per second quantity squared. Because cosines don't matter, the 2 doesn't matter. This is getting pretty ugly, so let's rewrite. This is meters cubed over second squared times second squared over meters squared. Flipping this one. And it is units of meters. That looks pretty good, right? Now every term has units of meters. Before I waste time doing algebra, I'm pretty confident I didn't screw it up. Is this making any sense? How's everybody doing right now? Thumbs up, thumbs down. Okay, okay. I saw a few sideways. That's good too. Keep our eye on the prize. Man, we're trying to figure out what L is. Are we going to have to do the quadratic formula? No. Why not? Every term has an L in it. So we can cancel one L, we can cancel one L, and there'll be one left. It looks horrible. If you're patient, this one should work. Okay, so let's write one more line here. Come on, negative L sign. If you want to race ahead, go. I'm going to try and clean this up a little bit. I'm not going to convert the sine over cosine just based off experience. So just trust me a little bit. Make sure that's right. This term I didn't do anything to. This one I basically canceled the V naught and brought the L out to the front. This one I squared every term inside. L squared, cos phi squared, V naught squared, cos theta squared. Still have a G over 2. So far so good? Now, hopefully, that's what I was trying to say, and that's maybe what you were observing, is one of the L's drops out. Agreed? So now I can see it better, like that. What was our goal in this problem? Remind me. Get L equals something. So what should we do right now? Isolate L. Ratio. Go. Okay. And just trust me, don't move anything around, don't cancel anything, and don't make this tangent theta, just because I know what's up, all right? Just trust me. You can do it any way you want, talk as much as you want with your neighbor, I don't care. There's many correct ways to get there, it's just algebra. Ooh, I like this. Everything for me has a minus sign, so I can cancel those. And I'm going to bring this up to this side and get the L on this side, like I like it. Get out of the way. All right. Yep. Just making sure I didn't copy something down wrong. Sine phi is all by itself. Cos phi sine theta over cos theta and all that other junk. So now I can solve for L. Just cross multiplying. by 2. That's what I'm going to do in this next line. I'm going to multiply this every term, right? Whatever you do to one term, you got to do to all terms. If I'm going to multiply the first thing by the reciprocal, I got to do it to every term. So I got to make sure I don't screw this up. Get out of the way a sec. There was a sine phi somewhere. Plus Jules, am I still on or am I off the whiteboard there?
No, you're on.
Thanks, appreciate it. Oh my gosh, that looks ugly, doesn't it? But it's just algebra. Don't freak out. Now we can try and clean some stuff up. And I want to do one step here. This is oftentimes why physicists will say the word show instead of prove. I want to go back to here. Look at this. This is a huge hint as to how to proceed. We know that the prefactor out here needs to have a v squared. I think this should be v naught squared. I apologize there. We know we need the 2 v naught, only one cosine, but both only one cosine theta, but both cosine phis and the g. So let's make it look like that, right? In this case, I'm going to get an L. Oh, maybe I could see. Do you see anything canceling out here? I see this. You see that? This cosine theta cancels one of those. And now we got to be careful. 2 v naught squared, only one cosine theta, g, and both cosine phis. That's the prefactor that we were told to factor out. Help me out. What's left here in the first term? What's left that I didn't factor out? Sine, what else? Sine of phi and a cosine theta. Gee. What's left on this other term? Is there going to be any cosine theta left? Brought out the one cosine theta. Well, there was only one left. What's left on this one? After you factor all that junk out, what's left? Cos phi sine theta. Gee, I wonder what this is. Does anyone recognize this from trig class? Sine A, cosine B plus remember those? If you don't know that, it's okay. Yeah, let's make sure I wrote it down right. If you look in your book at the bottom of the page, do you see some trig identities down there? So it turns out, look at the trig identities at the very bottom of page 76. Do you agree that that's the trig identity that we want? And this proves the result that we wanted to get? What do you think? So far, this is just a standard projectile problem, believe it or not. There's nothing fancy here. It seems really scary when you first start, but I'm trying to get you to just believe the system I'm telling you to believe. Isn't that a cool? This looks weird, but it's just algebra. Okay, are we ready for part B? Yeah, this is the fun part. Determine the angle theta that maximizes downslope range. So remember our initial goal that I said when I showed the demonstration? What we want to do is figure out which way to aim the cannon. Or let me go over to this board. Our goal was to figure out, all right, I want to make this as big as possible. And I want to vary the angle. So the idea is I want to make this big by adjusting the angle. What do we need to do? Say again, speak up.
Maximization problem.
Maximization, specifically, what do you mean? What concrete steps do we need to take? You said a maximization. What do you do in a maximization problem? Of what? What do we want to maximize? No,
L.
we want to maximize downslope range. Downslope range means L. So I got to take the derivative of L. With respect to what?
Theta.
Theta. So the idea is I want to max out L with respect to the launch angle. Got it? And this is where physics is a little different than your calc class because you got to read the word problem. It's not just somebody saying, hey, maximize this function with respect to this. You have to read the words and identify what you're taking the derivative of with respect to what. Once we take this derivative, what do I got to do to it? You said maximization problem. I'm going to put you on the spot. What do you do in a maximization problem? You take a derivative, but we don't just take a derivative. What do we do with it?
You set it equal to 0.
Yeah, set it equal to 0. Then what do?
Then you find where it's positive and negative.
I'm going to start with 2 words. You have to solve this. This is an equation, right? You take a derivative of something and you set it equal to 0. That's an equation. By itself, it's useless. We need to solve this equation for what? Theta. This was the trick. You take the derivative of something with respect to some parameter, then you solve for that parameter. And that becomes theta critical. You remember that? You probably called it like take dy dx, and then you got x critical or something, or f of x, f prime of x, and x critical or something. The idea is we're going to solve for theta. That becomes theta critical. Theta critical, you can plug in to get L max or min. Now, some of you were saying plus or minus. What do you mean by plus or minus? There is something that relates to plus or minus in here. It's just that's not the first step you do. What I want you to do is take the derivative, solve for theta, right? What does the plus minus step do for you?
Tells you when this slope is positive or negative.
True. What does that help you with? Yeah, or the second derivative test can get you the concave up or down. If the second derivative is positive, then your concave up, it's a min. If the second derivative is negative, then it's concave down, you got a maximum. Do you remember that crap? All right. It's been a little while, but hopefully this makes sense, right? Now let's look at this function. Does that look bad? Is that going to be tough?
Yeah.
No. It looks much scarier than it is. One of the tricks is we're taking the derivative with respect to theta. Which things in here are constants? Is 2 a constant? Yes. Is V not a constant? Is G a constant?
Yes.
What is phi? What did phi mean in our problem? Angle of the mountain. Are we going to be changing an entire mountain slope? Not unless we're really, really rich. Bezos can do that if he wants, all right? Theta is we're changing, right? How about this? Constant. Everything's constant except for just 2 terms. This is not nearly as bad as it looks. When you first look at it, you're like, I think I'll just change my major. But you shouldn't, right? One of the things about this class is you got to learn how to be tough. You got to have some grit and just suffer a little bit. And if you get used to that, that's why you're going to have a job and get paid, right? There's a reason they have to pay engineers. It's because you have to put in a little work. All right, so let's do it. Go. I'll catch up. I'm gonna do this on this other board over here, people on Zoom, so I gotta erase that board, then I'm gonna do it, okay? Talk as much as you want, work with your neighbor, look at the solutions, I don't care, but see if you can get it done. Writing that giant formula over here. Making sure I've got the equation written right before I start. I suppose I should have checked the units on that, but since we had the result, I knew we were right. I should have checked the units. I'm a bad person. I'm going to set all this equal to 0. Here's a cool trick, everybody. Factor out the constants first. Anything that you can factor out. I want better black marker. Factor out those constants. What's this? Oh my gosh, every marker sucks. This the one? Ah, thank you. On the right screen, yeah. Wait, cosine theta is not a constant. Here's a cool trick. When you factor out those constants, you can just cross multiply by the reciprocal, right? These constants are going to drop out, right? So said another way, if you have all the constants out front, this must equal 0, right? The constants aren't going to equal 0. This should equal 0. All right. What's the derivative of cosine? Negative sine. So I take the derivative of the first times the second. Right? And then what am I going to do here? I'm going to add cosine theta times the derivative of the second. What do I get when I do that? What's the derivative of this?
Cosine of
Positive cosine. Good. Whatever's inside times
the derivative of the inside.
the derivative of what's inside. Well, in this case, what is the derivative of what's inside? 1, because phi is a constant. The derivative of a constant is 0. The derivative of theta with respect to theta is 1. So it looks really horrible, but it starts to work out. Do you recognize this from a trig identity at the bottom of the page?
Cosine of A plus cosine of A.
We could call this A. We could call this B. this is A, this is B, what do we get? Is it A plus B or is it A minus B?
A minus.
Careful. I'm going to write down this trig identity here so you can understand how these symbols work. If you are not familiar with how these symbols work, plus equals, or sorry, plus minus is different than minus plus. Okay, what this is saying is, if you want to use the plus sign on this side, you have to use the minus sign on this side. If you want to use the minus sign here, you have to use the plus sign here. So there's a subtle difference here. So now I see my sine function has a negative sign on it. Am I going to want to use cosine A plus B or cosine A minus B?
Minus maybe.
Plus. Look at it, right? Do you agree? Let me rewrite this. This is cosine theta plus phi minus sine theta plus phi. That's what we got here. My claim is, look, I've got a minus sign right here. That means I've got to use the minus sign right here. Well, if I want to use the minus sign right here, I have to use the plus symbol. Here's the deal. If you're bad with trig identities, this is not, you're probably like shitting your pants. Don't worry. There's not going to be a shitload of trig identities and stuff. We just need it for this one problem so that I could, yeah. So in general, most of the test questions are not filled with trig identities, if that's what you're worried about. That said, do you agree this becomes cosine of 2 theta plus phi? Take a second to absorb that. Are you good with that? Thumbs up, thumbs down, just give it to me. Theta is like A, right? B is theta plus phi. So when I add them together, I get 2 thetas, right? A equals theta. B equals theta plus phi. A plus B equals 2 theta plus phi. Right? Am I losing you, or is this okay? What was true about this? This has to equal what? 0. What were we trying to do? Were we trying just to torture students? Might seem like that. That was not the goal. What was the goal here?
Find theta.
Find theta. Do we have an equation that has theta in it? How do we get it? Cosine inverse. Now, I'm running out of room. I'm going to erase the trig identity and do my work up here. We'll get a break after this problem. Don't worry. So I need 2 theta plus phi equal cosine inverse of 0. Just took cosine inverse of both sides, right? What is cosine inverse of 0? I'm not, you don't have to feel shame using your calculator. 90. All right. Is there another result? Yeah. You think 270 is going to be a good idea here? That probably corresponds to a mountain pointing the other way, right? We're doing a ski jump to the left. Just watch what happens here. There's 2 possible results here. Agreed? Help me find theta. Right? What do you think? Did I do that too quickly, or does that make sense? Oh, what did I forget? I should have divided phi by 2. I was in a hurry. Bad wrong. And we never would have caught that with a unit check. So, right, I divided both terms by 2, the 90 by 2 and the phi. Sorry about that. Wait a minute. Does this make any sense at all? We should check. Do you know anything about the angle that gives you maximum range when you're throwing a ball from a kid or from high school physics? When you're throwing a ball, what angle gives you maximum range? I heard 45. We see a 45 popping up here. What if the slope of your mountain was 0? Doesn't that give you that answer? If your mountain had no, mind you, what does this look like? Theta was the angle that you're jumping at. Phi was the angle of your mountain. In this case, if the angle of your mountain was 0, we're flat. 45 degrees is what you expect if air resistance is negligible. All right, so that's pretty good. What would 135 mean? What direction is 135 minus phi over 2? That's a mountain to the left. You see what I'm saying? 135 is over here. So if your mountain's going this way, you might want to use that result. If our mountain's going this way, we'd want to use this result. So both results make sense. Right facing mountain, left facing mountain. Okay. How else could we check this? I was thinking, how about we just do it? We've got the mountain right here. Let's do the problem live and then take our break. And then you guys you've earned that break today, right? All right, and so you two are right in there in the camera. And you know what I'd like to do this time, just so we can see it a little better? I'd like to pull this table out the way. You can scoot over there. Oops. Drop that book down there. Jules, can you see it all on Zoom? Thanks. All right. So what I'm going to do here is instead of launching this full speed, I'm going to launch it at a slower speed just so that it doesn't go over the edge of the ramp. So what do we got here? Our ramp is angled at approximately, let's say 14.5 degrees. So help me out here, class. The angle of my ramp, phi, equals 14.5 degrees. I don't know if you can see that on Zoom. A little bit. Okay, 14.5 degrees. So phi is 4. You just write it down. All right, figure out what the launch angle should be, will you? Is it big? Well, if it's 15, is that about what, 30 degrees? You agree? What's that? 37. Okay, 37.75. Wait a minute. This is 15, isn't it? Basically. 45 minus 15 is about. Oh, wait, we got to divide by 2. I screwed up that 2. So thank you. Okay, 30. How about just 37? Is that close enough? Thank you for catching that 2. For some reason, that 2 is not resonating with me. All right. You want to come up here and confirm the angle of this thing? Look on this side.
Wouldn't it be closer to 38?
Yeah, whatever. Okay, 30. It turns out, I know from experience, this gun doesn't shoot repeatedly. How about we say somewhere in the 37 to 38 degree range? Are you cool with that? I just know this thing is it's going to be like 2 degrees insensitive. So anywhere, somewhere basically between 35 and 40 is probably going to be the max. So, all right. So can you read that at all? Yeah, this one here. A little more. Good enough? Okay. So now what we're going to do is launch it. Can you go over there and just basically catch the ball? I have no idea. And so what you want to do, actually, don't worry about catching the ball. Look at where it lands and put your finger there. Got it? You see what I'm saying? So when it hits, try and keep an eye on where it lands. So we're going to shoot this at 37. Now I'm going to use the short range, so I have no idea how far it's going to go. I'm expecting somewhere in here maybe, but I don't know. I haven't done the math. We could, but we didn't. All right, ready? Oh, look, I got a bunch. Let's do it again. You know approximately where it's going to land, right? Yeah. Pencil mark. And then make sure you're out of the way for the zoom, but then immediately there. Don't you love teaching? Ready? Right here. Watch. Just keep your eye right there. All right. Okay, just put somewhere in here. Just put a big line or a circle. We draw right on the beam. Right in here. Yeah, okay, that's about there. So now my claim is, okay, back up a little bit. Now we're going to shoot this at a different angle. Let's go substantially higher. So let's go up to about 40 degrees, significantly higher. So this is about 40.5 degrees, okay? Let's see. And watch out, you're in the way for the zoom. All we got to do is see if it goes farther or less far. Ha! About the same, do you agree? But all right, so then let's go lower. Oops. Oh my God, I don't have to move it. 35. It's about 32. Okay. Try it one more time. Great. And so while this isn't necessarily the most dramatic, imagine if all these angles are giving approximately the same impact region right here. That's a sign that that's about where the maximum is. It's a lot of work to do one little problem, isn't it? Welcome to engineering. All right, let's take a break. Hopefully you got something out of that. All right, take that break now. Woo! Oh, thanks. I used to work night shift and then have to go to class in the morning. At one time, I literally fell out of my chair in class because I fell asleep and I fell out in class. Another time I missed my statics test. It was late for like, I got there 5 minutes before they ended and was able to scribble down and not completely fail. The old school. Students have it rough. I don't know, man. It's tough these days. All right. So we have a couple more topics in chapter 4, and I have a feeling we aren't going to get it all done in 45 minutes, but I'll just tell you what the 2 remaining topics are. So we have 2 more problems, 2 more types of problems that we want to look at in chapter 4. 3D kinematics, meaning we're going to talk about stuff like, let's say you have a position function as a function of time is some x of t in the I hat plus y of t in the j hat plus z of t in the k hat. That's one of the types of problems. Or similarly, you can have velocity as a function of time is equal to velocity x as a function of time in the I hat. So those problems are on page 77, and you'll see some of them on the practice test. Probably should do both of those problems on page 77. All right. Relative velocity, we'll talk about this at the end if we have time. But essentially, if you have 2 objects with one moving this way and one moving that way, we have a coordinate system like this, you could actually recenter the coordinate system on this one and set this object to rest. Now, keep in mind, these things should be separated very rapidly, so then we end up having to add the opposite of this arrow over here. And this ball ends up going really fast to the left relative to the red coordinate system. Now, to be clear, I'm going to talk about this one later. I'm just trying to foreshadow and introduce the 2 remaining topics. This is not sufficient to understand it. I will cover this more in a minute. Okay. So right now, I want to focus on these types of problems where we have position and velocity as a function of time in Cartesian coordinates. Okay. And then we'll come back and do relative velocity if we have time, or we'll finish it up next time. Maybe we'll start it today and finish it next time. And then we're still only a little bit behind. All right, here we go. Let's take a look at question 4.24. And in that question, you are told the following. Okay. And we're told in the following problem, this is our coordinate system. X is to the right, Y is upwards, and Z is out of the page. In case you don't remember cross products, X goes to Y, goes to Z. Whenever I write a coordinate system, I like to do that. We'll focus more on the cross products that we did a little bit in chapter 3, and we'll do it again in chapter 10, really hardcore. But for now, I hat goes to J hat goes to K hat. That was the wheel of pain, if you recall. The idea is something in the I hat crossed with something in the J hat goes to something in the K. All right. Well, when you look at this equation, I'm just curious. What's your gut tell you? Is this constant acceleration or not? What do you think? Is it obvious or is it not obvious? Why do you say constant acceleration? What's oh, so you're not, so you're saying it's not obvious then, is what you're telling me, right? Okay, you see something with a t squared and you're thinking, actually, that's really good. You're right, it is constant acceleration. What were you gonna say? Exactly. So what you want to do is not overthink this. For me, it's not like immediately obvious until I think the following. How do you get velocity as a function of time? We're going to take ddt of all that. And then how do I get the acceleration? ddt of that. Agreed? Now think about this. Is the stuff in the I hat going to affect the stuff in the J hat? Yes or no? Does the stuff in the I hat affect the stuff in the J hat?
No.
No, that's what all these silly demos I've been trying to show you are. X does not affect Y, does not affect Z, does not affect X. So that's why you could kind of look at it and say, well, when I take two derivatives of this, what am I going to get? 0. When I take two derivatives of this, what am I going to get?
T.
One derivative gives me 6t, the second derivative is going to give me 6. So that's a constant. What about two derivatives of this?
0.
So it is actually constant acceleration. We didn't necessarily know that right away. Let's take our time. Let me read the question now. Oh, okay. So this is kind of the big picture of what we're trying to do here. Let's start with question A. This is on pretty much every test or final or both. Every midterm, final, or both. Usually has some question where I ask you about units. Now here's the deal. When you see an equation written like this, usually this is how your calc book would write the equations. But there have to be units on this. So to be clear, when I write an equation like this, I'm assuming there are units. In particular, what are the units of this looking thing right over here? What are the units we assume for this thing? Meters. Why? What is this called? It's the position, and just to be clear, I'm going to say it's the position vector, right? So it's position meters. So what do the units have to be for each term? Meters. So, okay, so what are the units on 6? The units of 6 should equal meters. The units of -2t need to be meters. So that tells me the units of -2 are what? Meters per second, right? So the t gets canceled out. Or you could say it like this. It's meters divided by the units of t. Is that helping? We've got to be good at checking the units all the time. Okay. So what are the units of 3 in this case? Meters per second squared. And there's, you can tell that relates to the acceleration, but it's not the acceleration. Just because 3 has the right units for acceleration doesn't mean that's the acceleration. We know that there's going to be some derivatives and stuff. And what are the units of this -4? Meters. So far, so good? Before you do any math on a problem like this, you should understand the units involved in a problem like this. I cannot express how fundamental that is. This is why. You're going to be pretty good at doing math. You're not dumb. You're in this class. You know something, right? So the idea is you're going to be pretty good at doing math, but you will occasionally make mistakes. And if you don't know the units initially, you can't check the units at the end to catch your mistakes. Good? Enough on that? All right, so that's part A. Let's not overemphasize it, but make sure you do it. What is the initial position? Part B. What does that sentence mean? Initial position.
position when t equals 0.
Okay, what is position in this problem? R of t equals 0. Plug in t equals 0, and that's how you get the initial position. Is everybody okay with that? What do you get in this case? I think we get 6, 0, -4 meters. And I'm using this notation where this term is the I hat, this term is the J hat, and this term is the K hat. You could write it in this way. 6 in the I hat, -4 in the K hat. You could write it in this way. 6 in the I hat, plus 0 in the J hat, plus 4 in the K hat. I had a student once told me they really felt uncomfortable writing down the vector without all 3 components specified. I don't care as long as it's correct, right? Now on these, I would probably put units of meters, just because we know it's supposed to be in units of meters based off of all our discussion in part A. Dom, do you have a preference for these notations? In particular, do you care if they write the 0 or not?
I do not care. I got J hat.
Like you prefer this, and this?
No.
Oh, this one, right?
Yes.
Yeah, me too. I don't like writing 0 if I don't have to.
Don't have to write it, don't.
But
I
math
hate-
people,
I hate the first.
you don't like this one? Yeah. Now, the reason I never used this for years, the only reason I do it now is because we're coding a lot and I know you're seeing it in the code. Both Dom and I dislike this because this forces you into a Cartesian coordinate system. And then it turns out in dynamics and statics, what if we use latitude and longitude and other types of coordinate systems? So people think, oh, I'll just write it like this all the time. And I'm assuming that's why you dislike it.
Yeah. I got J hat. Radio.
ER, Theta, the, so there's different types of coordinate systems, and this is only good for your Calc 184 class or Python. Basically, yeah. So it has its use. Enough on that. All right, let's keep going. B. That was part B, wasn't it?
Yes.
All right, part C. What am I asking for? The initial speed? Okay, let me get a new whiteboard here. How do you get the initial speed? Okay, that was part C. Initial speed. He said the procedure is take the derivative of what? Just help me out.
Position.
With respect to,
Time.
so can I write it like this? Like that? Then what should I do? That's the first step. I want the initial speed. What do I have to do? I'm going to do that last.
Set the time equals to 0 again.
Yeah, set t equal to 0, and then somebody caught it. I don't know who said that, but that was right. I was trying to trick you and you caught it. Outstanding. Outstanding. So we need to get the magnitude of it because I said the word speed. So I'm not trying to trick you, too bad. These are just common things that show up in the real world. Sometimes you want to understand the speed. Now, somebody else said, get the magnitude first. Could you do that? Absolutely. So steps 2 and 3 could be interchangeable here. You could get the magnitude, then set t equals 0. Agreed? Okay, go. Ratio. Let's see, that's going to be -2 in I hat. The units we're assuming are meters per second here. Oh, I should be careful. No. I want to point something out here. This is bad. What I just did is bad. I don't want to put this meters per second on here. Right? I haven't plugged in what T is. This is a mixed formula, and we can talk more about that later. But now I'm going to plug, I'll take the magnitude first here, or whatever, or what did I say, set T equals 0? -2 in the I hat, and that's it, right?
Yes.
We can ignore the other terms. So now it makes sense to put on the meters per second. When T was here, we have what's called a mixed function, where there's some algebraic parameters and some numerical parameters. You've got to be careful with those. I'll address that at a later time. Basically, for us, we want to put our units on at the very end. So far, so good on initial speed. Okay. If you wanted speed as a function of time, a common exam question. We wouldn't plug in t equals 0. It would be, we'd get the magnitude of this. So we'd say the first parameter squared plus the second parameter squared plus 0, and then we got to square root it. Should I take the plus or negative root when figuring out speed? In this case, we would only need the plus root. I don't need the minus root. So we could write this maybe a little bit prettier. Wait, that's 4, isn't it? So if you wanted to do it that way, somebody had said, why don't I just get the magnitude first? Yes, absolutely. And then in this case, that would get you the speed. Oh, look, what did I screw up?
Make it positive.
What did I answer right here? What did I write right here? Is this the initial speed? No, this is the initial velocity. I had forgotten to do step 3 where I take the magnitude. I had set t equal to 0. And you can see it right here. Do you agree that this answer and that answer are not going to match? So don't forget, the magnitude is 2 meters per second. So that's the initial speed. Watch out. So did you notice how I caught my mistake? I reread the question. So a lot of times on your test day, you're going to know what to do. Most of you probably kind of said, I know what to do here. It's critical to reread the question at the very end to make sure you answered what you were supposed to answer. Shame on me. Okay, good. How you feeling on this one? So far, so good? Hopefully this is good from calculus class, right? All right. Part D, initial acceleration, magnitude and direction. Okay. Oh, look at part E really quick, everybody. Look at part E. Do you agree we accidentally just did part E? Write down the speed as a function of time. All right. Anyway, sorry, I just noticed that. So part D, let's get part D. We want the acceleration, magnitude, and direction. How do I get the acceleration? Derivative of velocity. Now, which function do I need to take the derivative of? Do I need to take the derivative of v of t, or do I need to take the derivative of v of t? The top one is the vector, right? V of t is speed, v of t is also. So again, we see that these little arrows, when you write them, have meanings. The I hats and the j hats have meaning. If you screw it up, I'll mark you down. Okay, so you got to make sure you get those arrows and be like super picky when you're reading the solutions. Don't just be like, oh, it looks about the same. Make sure it looks exactly the same with the right I hats and arrows and stuff. And if you're not sure, ask a question. Okay, here we go. When I take the derivative, didn't we say already we're just going to get 6 in the j hat? When you take the derivative of this term, drops out, nothing there, you're going to get it. Oh, what did I screw up?
Meters per second squared.
Got it. Always check those units. And then in this problem, do you agree we specified the magnitude is 6 and the direction here is j hat? And we've got the units. So this is all together. If you wanted to be clear, you could say A This is the magnitude with no arrow. And then if you want the direction, you could specify it as positive j hat. So this could be another way to write that. We are clearly specifying the size and direction separately here, somewhat indicated by the problem statements. Everybody okay with that? Yes, question?
So for the speed of time,
Yes, this one is the speed as a function of time.
so in that case, you get the magnitude, but also when you were just using the velocity function as the speed of time, you just like the very last result, you just took the magnitude.
I took the magnitude of this final result. So yes, to be clear here, right, if we wanted to get the magnitude of a vector, right, let's say our velocity vector was Vx in the I hat plus Vy in the j hat plus Vz in the k hat. In general, that would be an arbitrary vector for a. You agree? The magnitude V, sometimes we'll write it like this. We'll put these double absolute values on there for vector norm in a math class. I'm not going to be offended if you use single absolute values, but some math teacher probably will. Right? It's just do the Pythagorean theorem in 3D. Vx squared plus Vy squared plus Vz squared, like that. And in this case, notice there's no I hats anymore, and we're going to assume, since you're doing a magnitude, we're taking the positive root. Did that address your question or not?
Yeah, so I was just getting confused between the absolute value versus the maximum. I was thinking that you just took the absolute value of the two.
Yeah, they're very similar, right? Well, sometimes I'll even just say take the absolute value or magnitude interchangeably because the symbols even look very similar. But strictly speaking, when you get the magnitude, what are you doing? You're getting rid of the I hat, j hat, and k hat, right? Right? Notice there's no I hat, j hat, or k hat here. And you take the scalar components. That's what we call that. Just the Vx part. The number with the plus or minus and squared. The number with the plus or minus and squared, and the number with and add them all together. And notice the units should come along for the ride too. Is that good? Feeling better on that? Sorry if I glossed over that. Yeah, so when I say take the absolute value of that, if I said that, I meant to say take the vector norm or get the magnitude using this process. And so in this case, that's why it would be -2 squared plus 0 squared plus 0 squared. That's why I was able to just do it in my head. Is that okay?
Yeah.
Sorry, I did a bad job there. Other questions on that? That was a good one. Yeah. Right, if we're going to be picky about this, definitely pick me apart up here and ask if I don't make it clear. All right, good. Part E, I accidentally answered it right here. Here's part E. Speed as a function of time, because I happen to have it here, right? Well, we got velocity, and then you take the magnitude of it. The only thing you wouldn't do is set t to 0. So if you skip the step of setting t to 0, you get speed as a function of time. Is that okay? Okay. What's next? Oh, part F asks you this. Which is easier, getting distance as a function of time or displacement as a function of time? Based off your experience in my class so far and all these weird little problems that I've thrown at you, let's just go with your gut. Do you think it's easier to get distance or displacement as a function of time?
Displacement.
Displacement. Describe how you would get displacement as a function of time.
The displacement as a function of time would be
Or do you know any equations for displacement in general? Will I get this more?
the delta x or y equals the initial velocity times speed times 1/2 acceleration.
Oh, that would apply in this one problem because it's constant. You're doing the constant acceleration, delta x equation, delta y, etc., right? That would be valid for this question, and that's outstanding, but it's not valid in general. Let me just show you why this is actually really easy in general. So you're right for this problem. I want to show you an even stronger way. Displacement is delta R, right? Is this still on Zoom, Jules? I think, right? Thanks. in general, displacement is final minus initial, right? Do you agree? We know this. This was 6 in the I hat minus 4 in the K hat meters, right? And this is just our crazy function. It's just whatever it was. And I want to point this out. You could take this function minus these constants, and it's like the easiest thing ever. Agreed? Which is what you were doing. It was just a longer way to get there. Do you agree? Displacement is literally change in position. What is distance traveled? All the displacements, yeah. Well, do you agree if something reverses direction, we might run into trouble at distance?
Magnitude, or the absolute value.
I'm going to call it arc length from calculus class. Right? Did you do those problems in calc class? Aren't you glad we aren't doing them in this class? Woo-hoo! So if you want to understand this, that's literally what arc length means. And to be fair, the fastest way to do it would be learn the coding tricks I'm showing you and just add up all the displacements for each individual time step, and you'll get the displacement within arbitrary precision. So there's an example where you can do a numerical arc length. Anyways, I would love to talk about that, but I can't because we don't have time. Cool? There's a difference between distance and displacement. Displacement is easy. Remember the ski slope problem we had a question on earlier? Remember you were saying it goes up, then it goes down? Displacement was just, it started here and it went here. The displacement was negative L sine phi in that ski slope problem. We didn't have to worry about the arc length traveled. That's why displacement is easy. It's just final minus initial. Cool on that? This is why it's so crucial to actually get the words of displacement versus distance correct. Okay, I'm going to leave 4.25 for you to do at home. And I'm going to tell you right now, every single one of you will probably screw it up. You're going to think you know what you're doing, and there's one little trick hidden in there somewhere. So if you can get that one just fine, then I'm wrong and I'm a bad person. But almost certainly people look at that, they're like, I know how to do this. I'm not going to practice. You better do that one because I know what kinds of questions I put on my test. I know. Yeah. Does anybody see what's going to get you in that problem? Let's take a second to look at it. 4.25.
The K hat,
What about the K hat?
it's a fraction.
Okay, it's a fraction.
Well,
Okay. Okay, so that isn't even, I'm confident in your abilities to do calculus. I'm assuming you guys actually know how to do calculus. So that's ignoring the, yeah. All right, I'll leave it for you guys to find out. Okay, make sure you do it though. Just, yeah. Trust me, you should do that one. All right, I'm gonna erase the board. You can stretch for a second. We got 20 minutes left. I'm gonna try and briefly introduce relative velocity, okay? I'm gonna erase the board. You can take a second to look at it if you think. Right? Talk with your neighbor as much as you want. Don't just erase the other board, Zoom. You guys can keep working on that one for a couple minutes. Talk as much as you want. I'm not offended. I'm gonna try and get a simulation ready anyway, so I've still got another 2 minutes or so. Thinking around up here. I've got a minute while I get this fired up. Must be in the other one. Give me a second. Oops. There it is. All right. We've got about 15 minutes left here, so I was hoping, oh, let me do a screen share here. Oh, I see something in the chat. We were looking at 4.25 just a minute ago, but. All right. So I'm going to let you work on 4.25 at home. If you're really passionate about it, I'll help you right after class too when I have office hours. But I want to talk now about relative velocity here. So imagine we have two objects, a blue ball, which we could call B, a red ball, which we could call A. And actually, there's a third object that's implied in here. I'm going to call it the planet Earth. So the planet is like our coordinate system, okay? So first, I'm going to click this Earth button down here. And the idea is, let's say just imagine you're in a helicopter or a drone and you're observing people walking down on the sidewalk and they're going left and right. Okay, let's try this again. Does this do this again? So again, you're looking down on from an aerial view at people walking around, and one of them happens to be going in the first quadrant, and one of them happens to be going in the second quadrant. Well, imagine if instead of sitting with your drone at rest relative to the Earth. So imagine right now the drone is just sitting there. Let me run this one more time. The drone is just hovering above the origin, sitting there. And then you observe these two people going outwards. Imagine if instead you were on the drone and you tracked with object A. It would look like the entire Earth is going away from you and object B is going away faster. Look, run it again. Here's the Earth, right? The objects are going at 4 and about 4.5. If we run it with respect to object A, the object A would look at rest in the frame and all the trees and the Earth would be going the other way. And look at how fast object B is moving now, much faster, 8. Alternatively, what if we tracked object B? Right? The Earth would be going the other way. The ball would be going faster the other way. So the concept that I'm trying to introduce here is motion is relative. We generally assume, unless otherwise specified, you're at rest when you watch objects move. But that's not always true. Imagine you're in one airplane moving at one velocity, and there's another airplane moving at a totally different velocity. Both of those velocities are relative to the Earth. Well, it might be nice to know how quickly that airplane is moving relative to you, because that might help you steer more effectively. So that's the point of all this. Let me run this again. So again, the idea here is, depending on your point of view, you could either be in a coordinate system that's at rest relative to the Earth. You could be moving in with one object, like the drone following object A, or you could be moving with the drone following object B. It turns out this is fairly simple to deal with. We've got simple vector addition to handle this. But we want to learn some terminology so that we could do these vector addition problems correctly. Any questions while I have the simulation up here? Is the concept making sense? We want to understand the velocities of various objects, not just relative to the Earth, but also relative to each other. Okay, take a look on page 78. If you're curious, I could share that code later. I'll deal with that later. Okay, take a look at page 78. I'll discuss this and then we're done with relative velocity. Stop the screen share. I did, and I need to be on this other. There we go. So imagine trying to do this again. Relative velocity. You take your uncle and throw it. Relative. Oh. Ha ha ha. Very funny, Rob. Right there. Okay. There's basically one equation to know here. Two equations, excuse me. All right. And what do these subscripts mean? So let's just talk about this. We're going to talk about the velocity of object A relative to the Earth. So that's what the A and the E mean. And I don't care about the capitalization here. I'm not picky. Normally I would be, but in general, we should probably be consistent. I guess I wasn't. I apologize. Okay. Take a guess what this means. If I switch the subscripts, what does that mean? Velocity of what? Earth. And so the order of the subscripts is crucial in these problems. You can think of that in the simulations that we did. That's like the velocity of the coordinate system. Remember how sometimes we saw the coordinate system was moving around? This is like the velocity of the coordinate system relative to object B. So if you're in the drone tracking with object B, following, hovering directly above B as B moves around here, the coordinate system would be moving, right? This is our first crucial thing to understand. If you switch the order of the subscripts, you get a minus sign. If I move to the right relative to the Earth, I could envision that as everything on the Earth moving to the left relative to me. Got it? Or I'll say it this way because I have no idea what the camera right, left, and too much for my brain. If I'm moving this way relative to the planets, that's the same thing as the planet's moving that way relative to me. Okay with that? That's just what the minus sign means. And here is the vector addition equation that we see. Watch this. B, A, E. And there's many different ways to write it. Let me already use the same one that I used it here. Plus this. There are many different correct ways to describe relative velocity. I like to write this one. And here is why. My green marker stinks. Look at the letter E and the order of the subscripts. There's many different ways you can think about this, but this helps me work with these problems. The letter E is inside and it gets squeezed out right there. So the idea is I remember for my work with relative velocities, if I have an A with an E, then an E with a B, the middle variable that is repeated gets squeezed out and it helps me get the velocity of A relative to B. Notice that's what this would mean. Does that make any sense at all? If you write this vector addition equation, it will get you the answers you desire for the velocities of A relative to B. If you needed the velocity of B relative to A, you could switch it. Go ahead, question? Was that a question or no? Oh, so, oh, question there. My bad, sorry.
It kind of reminds me of like when you're doing an integral from like A to B, and you can break it into A to like C and like C to
Yes,
B.
so what I think what he's saying is it reminds you of this. You could do the integral from A to B plus the integral of something here and something here from B to C. That's equal to the integral from A to C. It is somewhat similar to that in terms of the memorization trick for it. It's a little bit different in terms of the implementation.
Yeah.
Yeah, but it is, yeah, I like that. And maybe that's why I like remembering it this way, is because maybe we're both familiar with this and it seems reasonable to remember them. Okay. So the idea is, in theory, should be a simple vector addition problem, right? How hard could this be? It's the most commonly missed question on test 1 every year. Here's what's hard about relative velocity for students. You have to read sentences and understand them and make sure, look at this, if you screw up 1 minus sign out of 3, you're always wrong, right? Almost always wrong. So in this case, it's crucial that you can read word problems carefully and look for the words and see if you can make the identification of what did I tell you, usually you have a chance at getting the problem right. If you can't read the words and get the right thing, like what if you accidentally say BBE is accidentally BEB? Or what if you said BBE is accidentally BBA? You're going to be off. Let's do an example problem, set it up. We got 3 minutes. Yep. Question? Oh, sorry. Oh, so good question. We are doing vector addition. In general, when we did chapter 3 problems with vector addition, the easiest way to do vector addition is exactly as you said. Split it into X, Y, Z components, or I hat, J hat, K hat stuff, and do it in Cartesian. So another thing that you very often have to do in these problems is switch the vectors from polar form, like you might describe them like this, with a magnitude and an angle, immediately go to Cartesian so that you can do the addition. Right? Do you remember that when we did vector addition problems? The first thing is get them all Cartesian form so it's easy. Absolutely. Is that good?
Yeah.
Right on. You guys want to try the hard one? Or the easy ones? I would like to save the easy ones for you to do at home, right? Let's just go full insanity. Let's look at 4.31 and a half at the bottom of page 79 and see why these actually get tricky. Okay, and we're not going to do the whole problem. We're going to try and set it up. That's the hard part. Okay, 4.31 and a half. Okay, I'm just going to get it up here. Okay, we are told in this problem, the train travels to the right with speed 20 relative to the Earth. To the right is I hat. This part, I'm going to just throw it out there. This is pretty easy. Velocity of the train relative to the Earth. Again, capitalization doesn't matter if you want to use uppercase, lowercase, whatever. Is everybody okay that we know the velocity of the train relative to the Earth? That's easy, right? Next, a player throws a ball with an initial speed of 40 meters per second relative to the train. What does that tell you? What piece of information does that give us? VBT, should there be a vector or not? Should there be a vector if I underline that word? No. See how it's subtle? Knowing a vector versus knowing a magnitude. That's what we know. We don't know the vector. Okay. Next. Almost out of here. We want to know what angle should the player aim to make the ball go 30 degrees relative to the ground. What are we asking for and what do we know? For example, what does this 30 degrees mean? Which angle is it? Okay, let me put it to you like this. Angles need to have subgroups too. So we know that theta of the ball relative to the earth should equal 30 degrees. Agreed? That's what we were told. We want this angle. What angle are we looking for then? What do we want to find?
Angle of netball.
Theta of the ball relative to the train. That's what we're looking for. Do you see how these problems can get tricky? We know one of the vectors in its entirety. We know the magnitude of another vector. We know the angle of the third vector. We're looking for the angle of the second vector. Got it? So what is your procedure? Get this in Cartesian form. There's going to be some stuff you know, some stuff you don't know. We're over time, but this is tricky. What happens is students are like, well, I know this is 40. I'm just going to make this 30. That's fine. I'll just give you a 0. It's cool. It's easy to grade. You got to get it right. I'd try to give you 1 point maybe, but out of 5, it's crucial that like you would get more points for correctly writing this down than just saying, well, he gave me some numbers. I'll use the numbers he gave me incorrectly. That just makes me want to puke. So if you're starting, so it's crucial to identify variables correctly. It's like half the battle here. All right. I don't know, Dom, anything, or Jules, anything you want to say? These are deceptively tricky because you got to understand the words. Get out of here. Have a good one. If you want, you can look it up. The solution is very detailed. If you look at the last 2 tests, there's been a relative velocity question that was pretty similar to this, and people tanked on it. All right. Oh my gosh.